All right, welcome everybody. We'll get started in 2 minutes. Welcome everyone. We'll get started in 1 minute. Right, welcome everybody. Welcome to today's educational program, The Power of Digital Twins in Industrial IoT, brought to you by IoT World and sponsored by ABB and ARC Advisory. I'm Lucian Fogoros, I'm the co-founder of IoT World, and on behalf of my team, thank you for joining. Our co-founder Carolina will monitor our online channel, so feel free to send your questions in a Q&A session or via the social channels, leveraging the hashtag IIoT World. I'd like to introduce our moderator for today, Greg Orloff. Welcome.
Thank you, Lucian. Good morning, good afternoon, and good evening, everyone. Now, before we get into today's session, please allow me to give those of you who are joining us for the first time a little background. IIoT World is a digital media publication that covers the economic and technological implications of the transformation taking place as industrial IoT proliferates throughout the enterprise. IIoT World combines journalistic coverage with data analysis to expose the stories, players, trends, and innovations that shape the IIoT. IIoT World was recently ranked by K-Core Analytics as the #1 global influencer on several topics that include industrial IoT, smart manufacturing, ICS security, SCADA, predictive analytics, and predictive maintenance. Our mission is to help companies create a culture of innovation and connect the smarts, industrial technology, manufacturing, sensors, and the CXO decision makers who seek these solutions. Now today we have an exciting panel that I personally have been looking forward to for quite some time, with representatives from ABB, ARC Advisory Group, and Corus. Simulation has been used in many years in the process world, but now the industry is taking this to a higher level. Historically, simulations and modeling were used for smaller parts in the plant or manufacturing world. It was also leveraged quite a bit for operator training. Now, an ever-increasing portion of the plant can be simulated as a digital twin, allowing for a virtual version of the plant lifecycle to be created to improve safety, productivity, and offer insights into the future failure modes, as well as opportunities for process improvement. When the simulation or the simulator becomes the control system master, the plant can reduce the risk of unplanned shutdowns and blackouts. According to Gartner, 75% of organizations implementing IoT technology already use digital twins as part of their systems or are planning to do so within a year. Now, peeling back that onion a bit, 13% of that 75% currently use the technology, with the remaining 62% planning to do so within a 12-month horizon. So essentially, this tech has gone mainstream. And to give you a snapshot of the key topics our speakers will cover today, what are digital twins and why are they the next big thing in industrial IoT? Will there be a digital twin for everything? How to simplify the process behind digital twin deployment? How to use digital twins to improve processes and safety? How digital twins help to reduce risk and unplanned shutdowns? Real-world examples of how digital twins are used in industrial automation. The current systems and solutions available for enterprises. So let's dive into our first session entitled Defining the Digital Twin. Our speaker is Mr. Will Hastings, Market Research Analyst at ARC Advisory Group. Will leads ARC's research in product lifecycle management, PLM, within the Digital Transformation Group. He is also a co-leader in ARC's additive manufacturing research, along with his German counterpart, Fabian Wonk. Product lifecycle management, or PLM, it is commonly referred to, has expanded beyond its traditional roots in new product development. As companies are beginning to harness the value of their data, the role of PLM is shifting from one of mostly engineering design and management to a hub for collaboration, connecting to all stakeholders throughout the life cycle of the product. This shift is being driven by technologies like cloud computing, advanced analytics, industrial IoT, and digital twins. These technologies often rely on PLM solutions as a source of context to derive insight or utilize PLM solutions as means of managing and distributing that insight across the organization and its value chain. In addition to following the PLM market from a quantitative perspective, Will also tracks these and similar trends as they relate to the overall theme of digital transformation. Prior to ARC, Will worked as a mechanical design engineer within the automotive industry. During this time, he focused on new product development and cost reduction projects. Will, I know our audience is keen to hear your insights, so please, the floor is yours.
Thank you, Greg. Also, thank you for that wonderful introduction. So let's jump right in. So my presentation is called Defining the Digital Twin. And so I'm glad you mentioned my focus or one of my primary focuses at ARC is product lifecycle management. So again, that's all the tools used by mostly discrete engineering companies to design and manage the data associated with their product. However, over the past year or so, I've been tasked with covering digital twin, and what you'll find throughout my presentation is that that's a very wide scope that contains a lot of technologies and a lot of domain expertise within those different technologies. And so my position as the digital twin analyst at ARC is not necessarily to dig into each one of those domains or technologies at a very deep level, but find a way to describe digital twin so that all the analysts who touch on it within ARC, with the markets they follow and the technologies they follow, can have conversations with each other and with our clients about digital twin in a more cohesive manner. And so that's really what is going to be reflected within this presentation. So to start, there are many different definitions of digital twin. If you Google it, I'm sure you can find dozens. There are a lot of similarities across these, which I've tried to highlight here. So terms like digital model, real-time, optimize, physical asset, context information, modeling, Internet of Things, run simulations. And depending on the industries that you're focused on or the applications that are being discussed, these definitions tend to shift their focus or the emphasis to one side of the idea of digital twin, the simulation side, or the IoT and the real-time data collection side. And even within ARC's own publications, there are some varying definitions of digital twin. Again, that's depending on the topics being discussed. And that really could include anything from product design to supply chain management. And so I believe, and I think most people who I talk to have kind of come to the conclusion that a few sentences isn't really sufficient in a description to have a foundation for a meaningful discussion of digital twin. And so what I'd like to do is look at where these definitions overlap and find a way to build a baseline for a more productive discussion, regardless of the industry you're in or the specific application that you're using a digital twin for. So this is kind of the simple visual summary of what a digital twin is as ARC defines it. And so, of course, you always have to start with an underlying physical asset or process that you can make a twin of. Within the digital twin, you have the digital model that is a reflection of that asset. This provides your contextual or characteristic data. Feeding the digital twin is real-time data coming from that asset or process, and this explains the operational states or behaviors. And then finally, something that's not as clear, especially to people the operations side or the engineering side, more so relevant to people in IT is the concept of an information model. And this is really the information architecture that integrates those first two elements. And then on top of that, and also sometimes within it, there are different analytical tools that can be used to capture insight for the digital twin or actually act as part of the digital twin. So for the next few slides, I'm going to step through each of these elements to give a little bit more detail, some examples of the technologies within them, and how they're used as individual parts within a complete digital twin. So the first element, which really provides the baseline for the digital twin, is the digital model. And this is really the contextualization and predictive capabilities of the digital twin. So here's defined as the model which is sufficiently complete to predict the behavior and the performance of the physical object over a time horizon that's useful for its industrial complex. So you can really think of this as the DNA of the digital twin, which with that DNA you can use to create a replica of that asset or that process. And so I like to think of these in two different ways. Part of the technologies provide the context. So we're talking about 3D models or even 2D or 1D models, maintenance procedures, bills of materials, even things like product or process specifications. These are the things that the engineering group within the organization might create in order to define the product or the process before it's even begun its life cycle. And then on the other side of the coin is the prediction and predictive capabilities. So these are things like process or physics simulations, control models, even things like logistics simulations or predictions around budgets and things like that. And so some key points here to think about are when you're building your digital twin, what kind of prediction complexity are you looking at? Are you trying to predict the behavior of an entire plant, or are you trying to understand maybe the failure mechanism of a beam within a piece of architecture or building? And then another question is, how important are the accuracy of these predictions? And so as you're trying to optimize a process, maybe if it's very unoptimized, the accuracy might not be too critical. But as you get closer and closer to an optimized process, that accuracy becomes fundamental to actually achieving your goals. And then the last point is the value of these predictions. So you can build a digital twin and you can have a very complex modeling and simulation, but unless you're finding some business value out of it, then you're not really getting out of the digital twin what you should be. And so kind of wrapping this up, what you really want to think about when you're considering this element of the digital twin is that it's really the engineering technology side of the digital twin. Next, we have the real-time data, which is the behavior and the history. So this you can think of as the element of the digital twin that really tethers it to reality. And so without this, you have a simulation which can be incredibly valuable, but this data is what makes it so your twin actually reflects the asset or the process that underlies the digital twin. And so this relevant real-time data is collected, and it must be collected with adequate fidelity to compare the model predictions with the operational performance. So this includes data types like process data or machine health and maintenance, obviously control data, even things like environmental data and schedules can be used to facilitate the digital twin. So some key points here, and something that I think is very important to highlight is the context of real time, and that really depends on what your digital twin application is. So if it's a process like an oil refinery, maybe real time is down to the second or even faster. But some examples of digital twins that I would call real-time data that is on the order of days or weeks are digital twins for a construction process. So when companies like EPCs are building a new plant, there are applications now where they have drones that fly around and scan the construction site once every couple of days that provide feedback to the EPCs to tell them where are we in our process and how does what we've built match the designs and the drawings that we have in our engineering phase of this site. And then part of that, of course, is implementing data collection. So what assets do we need to connect to the digital twin? How do we need to connect them? What type of data do we need to pull from them, and so forth? Part of that is determining the fidelity and volume. So is it necessary to have high fidelity and high volume, or can we get away and create accurate predictions and have an accurate understanding of our operations with lower fidelity, lower volume, and save in costs in terms of cloud computing and so forth? And then finally, a key point is ensuring data quality. So maybe you've hooked up all your assets and you have real-time data coming from them, but in order for your simulation side of your digital twin to be accurate, you need to understand and be sure of the data coming through and its quality. So this really coincides with the operational technology side of the digital twin. And the last element is the information or data model, which is the integration and the reconciliation of the two previous elements. And so the information model, as defined here, formalizes the relationship between the models in the simulation and the data. And what this does is it acts as the single source of truth for your operations and can be used to ensure that the digital twin model is routinely tuned to reflect the status of the underlying asset. So again, I'll refer back to the example of an EPC using a drone to capture 3D data of a construction site. So in the early engineering phase of a plant construction, you might do something like clash detection to ensure that different components of a plant don't interfere with each other during construction. Now, throughout the construction, things may move around and may shift. And what you do is you use a drone to capture the context of that construction site and relay that back to your digital twin. And you can then compare your digital twin as designed with the as built to ensure that no, we're not going to get a clash. Or if we are, that information can be then sent to the various stakeholders in the construction and then be addressed before issues cascade. So this provides identification and integration of the various data points that are coming into your digital twin. It also creates properties and relationships and allows for operations on your digital twin. And then underlined here, and as described earlier, is the concept of synchronization and reconciliation. And that's where you update your model to reflect the real underlying asset as it goes through its life cycle. So key points here are data structures. So that's being able to integrate your unstructured, your structured, and your semi-structured data. Governance, so who can see the digital twin? There are a lot of applications that are starting to be adopted where companies are opening up specific sets of data of their digital twins to suppliers or to end users. And that's something that allows for greater service capabilities, but it's also something to consider in terms of privacy and data ownership. And then finally, again, tuning, which relates to that concept of synchronization and reconciliation. And so I think of this aspect of the digital twin as the information technology. And so going through that, we have the engineering technology, the operational technology, and the information technology. And so when I think of the digital twin, I really think of it as the culmination of that concept of IT, OT, and ET convergence. So now talking a little bit about digital twin maturity. This is often difficult to talk about broadly, and that's because at least right now, digital twins are built by the user and not bought by the user. So there are a lot of examples of technologies that are out there, simulation technologies, IoT technologies that facilitate the creation of these digital twins as defined earlier. But in the end, a lot of the development and the construction of the digital twin is down to the end user to piece those technologies together. And so when we're talking about maturity, there are several key topics of maturity as they relate to the digital twin that are also associated with the maturity of, say, IoT and analytics. And so these are things like governance and data management, modeling and simulation methods, deployment and use, as well as the operational and infrastructure side of things. So how are your assets connected? How is your intelligence distributed? And of course, how is security being applied? And all these challenges are very specific to the industry that you're in or the application you're trying to use your digital twin for. And then finally, it also relates to the type of digital twin. And so ARC in our research have really found that there's two fundamental types of digital twins as they relate to projects or performance. And so here in this cycle shown here, there's build and model, connect and collect, analyze, execute and optimize, and innovate. And within that cycle, there are two cycles. So the outer loop would be the project digital twin, and that is more focused on the creation of an asset, the construction of a plant or a process. And then with that inner loop, you have the performance digital twin, which is associated with the ongoing optimization of the performance of an asset or the performance of a process. So on the right here, the project digital twin, some key elements to it and some things that it enables is the acceleration of program timing, the increase of product fitness, reduction of costs across the project, and it also provides a performance baseline for that end result. And on the other hand, you have the performance digital twin, which is used to optimize operating performance, ensure safety, and create and optimize services. So here's how those project and performance digital twins look when you align it with a plant lifecycle, as well as some applications that are enabled by it. So I also have here examples of greenfield and brownfield projects, digital twins, despite the fact that as of right now, they are mostly associated with the development of greenfield projects. They can certainly be used in the process of modification or modernization of your plant or process. So when we're looking at the beginning, plan, design, and engineer and construct aspect of a plant life cycle, you have a project digital twin, and the applications most currently associated with that are plant process design, plant construction, and virtual commissioning. And then as you move into the performance digital twin, the operate and maintain life cycle of the plant, you start incorporating things like operator training, process optimization, and asset performance management. And so one important thing to remember is that the virtual assets created during a project digital twin can be utilized during the life cycle of the plant as part of that performance digital twin. So despite the fact that there are somewhat discrete sets within this twin type category, it should be noted that there is a lot of overlap in terms of how these can be applied and the assets that are used to execute them. So I would like to take a moment to talk about some of the markets that are driving digital twin technology adoption. When we're looking at the industries, really the largest markets are the process industries, so oil and gas, chemical, and power generation. These are areas where even small increases in optimization of the process will result in a lot of cost savings. Also, engineering, procurement, and construction, EPCs, are utilizing digital twins, as explained earlier, to facilitate the construction of plants and also as a means to ease the handover process to the owner-operator. And then when we look at discrete industries, digital twins are being adopted, not as quickly, but they're still being adopted, mostly in the advanced discrete industries such as aerospace and defense and automotive. And these are mostly in industries and at sites where there's really advanced engineering and manufacturing. So looking at some of the key technology trends that are enabling digital twin, these are trends that are really highlighted in a lot of the work we do here at ARC. From the digital model perspective, there's building information modeling, digital manufacturing, simulation technology really across the board, and 3D scanning and photogrammetry. If we look at data acquisition, the industrial Internet of Things is really fundamental to providing that real-time information aspect of the digital twin, as well as edge device technology and 5G communication. and then finally the analytical tools that facilitate the simulation side of the digital twin. So we have machine learning and big data analytics, and underpinning all of that is cybersecurity. So the last thing I'd like to touch on is really the considerations for a digital twin initiative. So my first point here, the economy of data. It's important to realize that the digital twin is not a race to see who can collect the most and precise data, or you know, the greatest volume and fidelity. And it's really about determining the necessary volume of fidelity needed to drive the application. In terms of collaboration, there are many different technologies associated with the digital twin, and so that requires a lot of domain expertise to build, maintain, and as well as utilize the digital twin to its highest degree. And then also from a data governance perspective, which I touched on a little bit earlier, it's important to maintain the integrity of the data, provide available data across the enterprise, and also secure that data. And then from a scalability perspective, when you're implementing a digital twin, remember that, you know, as processes evolve and new assets are incorporated, there should be a modularity aspect to your digital twin to incorporate those new things, incorporate new tools such as analytics, and also be prepared to open up your digital twin across the enterprise for more uses. Thank you.
Thank you, Will. Excellent presentation. I thought a couple key points on this too. It's not a sprint, it's a marathon, and the quality of the data. And I also like the nuance of adding the modularity factor into this to incorporate new and upcoming technology and parts into the process. So we're going to move on now to our second session today, which is entitled Simulation and Digital Twins for Increased Safety, Productivity, and Efficiency. And we are joined by two speakers from ABB, Ms. Elise Thorud and Mr. Lars Leodum. Elise is the Global Product Manager, Simulation and Digital Twin at ABB. An experienced global product manager with a demonstrated history of working in the energy industry, Elise is skilled in leadership, technology planning, sales management, and product management. She's an experienced information technology professional with a Master's of Science focused in information technology and cybernetics from the University of Oslo. Lars is a sales solution architect at ABB. A chemical engineer by pedigree, Lars also possesses a wide scope of international experience from the whole product and solution value chain spanning R&D, product, and product management to sales. In his current role, Lars supports ABB's local business lines in order to strengthen the global digital business within the expert field simulation and digital twin. The solutions are based on ABB simulator product portfolios and part of the industrial automation business energy industries business line. Elise and Lars, the floor is yours.
Thanks, Greg, for the very nice introduction. And Will, thanks for a very interesting presentation. So now I will start the presentation. So we come from ABB, and ABB is a technology company. And we are big within automation and power generation especially. Our company was funded in the start in the 1890s when we started producing transformers. 100 years later, we started with giving the operator a better operator environment with a central control room, so it was possible to have a good overview to how to control a production plant producing a specific product. Today we have come very, very far with giving a collaborative environment for operation, for operators and engineering personnel, and also to add on more advanced services like cybersecurity and process performance for optimizing a process. We also see now that we're also moving on to a more cloud-based engineering environment, making the engineering more efficient. And we also look at artificial intelligence and big data analytics to provide more value to our end customers. From ABB perspective, from an industrial automation perspective, we see that there are several digital twins that can exist and coexist. It is a digital replica of a plant-wide configuration, behavior, and state. It can be a digital twin for assets, all assets on the plant. And what we see is that many digital twins can vary over time, and that the plant has many digital twins in the plant life cycle. The digital twins are often tailor-made for specific purposes. You can have generic digital twins, perhaps, but mostly they have some kind of a fidelity, either high or low, being very accurate, can be used for testing and for operator training, connected to the control system and such. And what we see is that some digital twins, there are many, but some of them can actually be connected together and communicate and run as a life cycle simulator. ABB has been in the simulator or digital twin technology for many years. And it is specifically in these segments that we are globally in oil and gas and in nuclear power and waste. It started in the early 1980s, where nuclear power wanted to have simulators for their plants, specifically for safety purposes, and to train their operators. Oil and gas was not uninterested. Very soon after that, they wanted also to look at the simulators and digital twins, how these could be used for oil platforms, for example, for operator training. It was a shift later when Microsoft technology was made more available. That meant that also simulators could be used for other segments, like, for example, fossil power. Prices went down on simulators, so now it is more accessible. And now we see also that with renewables, how to add, for example, windmill to an existing oil and gas plant with gas turbines, how should that be done in a good way to ensure the power production. We see a big market pool for digital twins. And these are examples from clients that we have. So there are process digital twins with different properties and features and what they can offer. For example, predict deviations, look at environmental aspects and energy consumptions and advanced process control, for example. And the output of these can be given to consumers, for example, to production planning, how to optimize production planning and what is the status of the production planning, should something be changed to meet a target. For operations and maintenance, the life cycle was gone through for the plant by ARC just now. So this is a typical plant life cycle from the start, the concept phase, and during via feed, engineering, commissioning, startup, operation, to modification. And here you have digital twins. You could have one or several, and then you use a simulator or digital twin, a process model, for example, here, to verify the concept and to calculate what equipment you would need to have a specific production for the planned plant. So looking at the process, electrical and control system digital twins, which is important for us in process automation, offering value to our end customers. For a plant, it is a plant control system, which is controlling the production of a product that is the process. And for example, the control system decides whether a valve should be closed or to stay open. Then if you take a copy of the control system and the operator displays and copy that to a simulator and create a digital twin of that, and you combine it with a process model, which is then a digital twin of the process devices, equipments, and the dynamics, then the control system on the simulator would control the process on the process model. And what makes it a twin? So the digital twin for plant objects would contain data, so it is made available for the operators, so the operator can control and can also perform a good asset management. The control system digital twin would run in simulation mode and have enabled versions of the control system so that it can run in simulation mode and can be used for testing and operator training. And testing is to test the control system. And you can run faster and slower than real time so that you can debug, for example, or you can increase the level in the tank a bit faster than on the plant. And you can run scenarios so you can train or test the same thing over and over again. But this will need to be connected with a process model or some kind of dynamics of the process and the electrical network, so that you can look at the plant behavior as a plant digital twin. And then we come to the plant life cycle again, from design to operation. And then the lifecycle simulator or the digital twins that forms these lifecycle simulation will be used for design. And when you can combine the process model with the exact control system that you would have on the plant before it is taken into commissioning, you can do a virtual commissioning here, so you can check the control system schema, the control system diagram, that the control system is actually operating and controlling in the correct way as planned. And there can be one or there can be several simulators, there can be several digital twins. And how can these digital twins solve some issues that process industries have? So what is seen is that 5% of the annual production of the worldwide process industry is actually lost every year because of lost revenue and due to unscheduled downtime. And 80% of these shutdowns are preventable. And what is seen is that 40% of these can be caused by humans. So that means that can we help the operator so to avoid these issues? And there we see that, for example, the operators can be trained, and they can be trained on the simulator or a digital twin of the plant that the operator is operating. You can also increase the automation level, so the operator doesn't have to do so many interactions, but still the operator needs to rely on the automation system that it is working and know that it is working. That can be done on a simulator with the exact same control system as you have on the plant, and also with the exact behavior of the process dynamics. ABB has actually a kind of a hidden gem of a digital twin in its control system. It's called an aspect object. And what that means is that for every object that you have on the plant, for example, a motor, it has a digital twin aspect object that contains all the information that is relevant for that device, for the operator or for the engineer or maintenance personnel. So then you can have one place where all information is accessible, for example, alarm limit configuration. If you have had an alarms lately, you can look at trends to see how this motor has performed, how it is producing, what is the power level. And this gives the operator a very, very good effectiveness because he has seamless access to information in one place. And for engineering efficiency, it's really, really good because the engineer, she can look at the organizational structures and have object-oriented engineering and look at the libraries, and everything is connected together. And then the operator has the same access to the structure, this digital twin, as the engineer or the maintenance personnel. And this gives a good setup for supplying information for more analysis. And with an extended automation system that we have, all this can be connected together, these devices with the control system, and it works seamlessly together. And it is an integration platform where systems, applications, and field-based technologies can be brought together. And it allows for execution of different strategies in one common environment. So it's really easy for the operator to have an overview and to perform the right actions. For example, to look at the condition monitoring. Do we need to do some actions on a valve, for example? Is it closing too slow? Do I need some maintenance, for example? And can have all these actions available in one place. And we have talked about process, and of course process is really, really important, because it is about process dynamics and how to produce the correct amount of a product. For example, if it is oil, or it could be a chemical substance. And we have talked about that you can have that is a digital twin for the dynamics, and you can, when you connect this with the control system and the real HMI, you have a really good updated digital twin. If you combine this with an electrical model, then you take it even a step further. If you add with a simulation of the electrical network with the generators and the electrical motors and the breakers, then you have even more of the plant information represented and can take actions. The operators can take actions which is according to full plant information, and avoid blackouts, for example, knowing how much power is needed to drive the different pumps and the devices needing energy. And without electric model, actually 30% of the plant information is missing. So here you have a true plant digital twin consisting of the 3 digital twins, so to say. ARC mentioned a project digital twin, and that was really interesting because that fits with this slide. So how can digital twins maximize benefits for the project life cycle and meet the client expectation to meet the dates to finalize commissioning? It starts, for example, in the design study phase. If you could use an electric model to look at which motors to choose for your plant to be able to produce the right amount of for example, pulp that you need for is planning to sell for your plant, then by not oversizing your motors, for example, and making the ones, choosing the ones that would make the most optimal meeting the specification, then we have seen that, for example, can reduce capex by 20 to 25%. On one specific plant, we had a simulator with a process model from Kongsberg Digital and with ABB control system, and there we did process performance optimization studies and saved a couple of thousand hours before commissioning by looking at the process optimization studies and the control system design and the starter procedures and the operator procedures. So then now they see that they saved actually 40 days or reduced the downtime. They had a better startup and had fewer trips. So looking back at the number where we say that 40% of the incidents cause shutdown, this is an example of 40 days reduced instead. because simulators were used in a good way for process optimization. What we will do now further, we have an R&D project together with Corus, is also to look at not only the training simulator and engineering simulator, but also what could we do further now? Could we bring the simulator more closer to what is going on cyclically on the plant? When should we do an as-built? So now we're looking at taking an online look at the plant, make an initial condition, a state, and take that onto a simulator, a digital twin of the control system and the process model, and see, should we now update the simulator, what would be the best time to do that, and then we can plan that with the client. So that is really exciting, I think, and also then we can go even further with optimization and studies. Here is an example of one of our really good success stories. It was a simulator for a natural gas processing plant in Norway. It's really, really huge. And they started using simulators early in the phase. And actually just during design phase, they discovered that a compressor was designed too small. And that would have been really, really critical to discover after the real commissioning. So they can then phone the maker of the compressor that it needed to be larger and to agree on a better specification setup. This simulator is using the company is using the simulator regularly for operator training, and all the control system changes are tested on the simulator. Actually, the simulator is a master for the control system. So when there are process changes, both the process model digital twin and the control system digital twin is actually the master of the setup for the target system. And then digital is real and real is copy. We see also that operators are regularly trained, and the benefit of this for this customer is that they have not had any unplanned stops due to control system problems in the last 6 years. And they had an issue, but that was because they had done some minor changes and didn't think it had any impact, but it had. So they have taken this to really high level. They have procedures for how to use the simulator for every step for this plant. For this plant, they had a full virtual commissioning with these digital twins and saved a startup time of 3 weeks, which would mean a lot of money. So you're talking a couple of $100 million. So that's really a good example of and getting money back for this investment. So this is the latest slide here. What would be the future for digital twins, and where are we now? So what was the situation earlier was that the simulator was used for specifically for operator training, and it was high fidelity, one simulator per plant. Very often, and the whole plant could be represented on the simulator for testing control system and being transferred to the plant to verified. Now it is more like you have more than one simulator, you have much larger scope, the whole of the production plant are taking in regularly for testing and operator training. You have engineering simulators, and you can make data available in real time everywhere. And you can combine different kind of digital twins, the high fidelity electrical model with the process model digital twin, and you can also make use of cloud to exchange information for engineering and do training like web training and so on. And we also add renewables like wind and solar. So that is happening now. And a lot of partnerships are going on. And in the future, it will be really, really nice. I'm very excited about that because I think this is really good technology to work on. It has a high impact for environment and for energy, how we can find the best solutions. So in the future, the actual plant state will be synchronized to the simulator, and the clients will have an enterprise approach that all plant can be overviewed for decision making. And for example, you can have teams working together, you can have interaction between plants, and you can take a more overall enterprise decision and have a more overall perspective. So it will be like a more holistic simulator, for example, with more digital twins working together. So this is the future. Thank you very much.
Thank you, Elise, for sharing those great insights. I love the example of the North Sea's natural gas application. And it just exemplifies to me the advantage of using a digital twin right out of the gate. Make sure you got the right equipment in the right place at the right time, and also down the road, it keeps your process optimized and you're minimizing downtime. So thank you once again.
Thank you.
We're going to segue now into our third and final presentation of the day, and it's entitled Digital Twins. And we're going to again be joined by two speakers, this time from Corus. Greg Deerwater, who is the Vice President of Business Development, and Philippe Thébout, Head of Sales for Corus's Oil and Gas and Chemicals business. Greg is a trained chemical engineer with a broad background in developing, delivering, and marketing advanced solutions globally to the process industries over the past 40 years. His industry experience includes upstream, midstream, downstream, specialty batch petrochemical, and energy and utility sectors for complex sales, SaaS, consulting services, and real-time process manufacturing solutions. Greg is experienced in advanced solutions, including process optimization, engineering, IT, information systems, simulation and controls, advanced process control, or APC, and the online manufacturing systems. He also leverages a focus on operational excellence and human performance improvement through the use of operator training simulation, OTS, combined with cognitive psychology, training program development, and cloud deployment. Digital twin research for process industries is a current research and development interest of Greg's. His professional experience spans petroleum and chemical manufacturing, engineering, automation, process licensing, software, and consulting companies. He's currently leading business development activities for Corus's hydrocarbon division, delivering high-fidelity dynamic operator training solutions. Philippe is a chemical engineer with dual masters in business and technology innovation management. Philippe has more than 20 years of experience combining international business development, engineering, sales, and technical consultancy for process engineering and real-time dynamic simulation. He's currently leading sales activities for Corus's hydrocarbon division, delivering digital twins, high-fidelity virtual process plants for what-if studies, control and safety system virtual commissioning, support to operations, and operator training to the oil and gas and chemical industries. Greg and Philippe, please share some of your real-world application experience with us. Gentlemen, the floor is now yours.
Thank you, Greg, for that wonderful introduction, and I want to thank ABB, Elise, for those great use cases, which sort of parallel and align to our business very well. So there'll be a little bit of redundancy, but I think everyone's getting the idea where we're going with automation vendors and OTS vendors in the digital twin space. Pardon me here. There we go. So today I want to answer one question. Basically, how Corus digital twin solutions can be leveraged in your company over the life cycle of your continuous manufacturing processing assets. That's a long sentence, but a couple key words in there. Digital twin solutions are leveraged across the life cycle of your plant assets, and they are continuous plant assets. So that's my goal. And first, a little bit about Corus. Corus has been around since 1966, and we have three divisions: in nuclear power, rail transportation, and the hydrocarbon processing industry. And as Greg mentioned, I represent the hydrocarbon processing industry division of Corus. So I'm not going to speak of nuclear and rail specifically, although we do have a couple applications there. Corus is characterized as being global, independent, dedicated to dynamic simulation. It's all we really ever do. We don't have any other thing going on, and we're very financially stable. We have digital twins of various types, standard models that have come out of many years of project experience that are on the shelf that can be repurposed for operator training or doing digital twins of various chemical manufacturing processes. We have custom OTS solutions, which are basically the custom models that are integrated with control systems that are delivered to clients as part of instrument modernization projects and new construction. We have 3D technology, which is immersive, first-person avatar. We have augmented reality, virtual reality solutions. We have training as a service that's delivered over the web. Our technologies are called Indus Plus and VESA. And we basically get involved in the services of providing our customers plans, master plans for how to go forward in a project. We do projects, we do software maintenance, we do annual support contracts, and that's all I want to say there. I apologize for coming in. Where's the little clicker thing? Okay. So why are we here? Well, we were invited by ABB, our long-term partner, to participate in this ArcWeb and IIoT range conference. So thank you for that. I will explain a little bit about us and them, and I want to cover digital twins and the uses of digital twins within the context of our business, give some project examples, and then basically put a picture up there which represents the ultimate digital twin and some of the current and future elements of that solution. As I mentioned earlier, we started, if you go left to right here in this timeline, we have over 50 years of innovative experience. Now, what I want to use this timeline for is an opportunity to kind of show our DNA, but also introduce some of the industry trends that have been popping up over the last 20 years. So as I mentioned, we started in 1966 delivering analog simulators to the power and process industries. Notice the sideburns and the double knit pants and the electronic analog panel board. It wasn't electronic, it was a panel board there with the analog instrumentation. So it basically looked just like the actual control room. It was made of metal. It was delivered, and these were used offline to train operators on how to operate boilers or distillation towers. A lot of iron. In the 1980s, advances in computing technology, platform, and software spawned many software and services firms, including Corus and Rail, Nuclear, ABB Simcon, and Oil and Gas, RSI downstream among them, as well as OSI Soft, and a lot of companies. You'll find a lot of companies were actually founded in 1980 in the software and services business. As you go down the timeline, you'll see that DCS automation companies, you know, with the advance of solid-state electronics, and that electronics control systems were replaced by distributed control systems. And then as you go down further, you see that Microsoft gets into the picture, and we were able, in the middle of this picture, to start delivering full training simulators that were implemented on Microsoft platform and digital, using screens that match the operator interface, which had gone from panel board to screens. And as you go further to the right, you see our future. In 2003, the term digital twin came into the lexicon by Dr. Michael Graves of the Florida Institute of Technology as part of his research into product lifecycle management. Some of the initial applications in 2003 and forward had to do with NASA and so forth. In 2011, the term Industry 4.0 was publicly introduced in Germany, and Industry 4.0 by a group of representatives from different fields such as business, politics, and academia. So Industry 4.0 and the Internet, industrial Internet of Things have basically enabled the implementation of digital twins. I don't know if, I guess people know this, but GE coined the term industrial internet in late 2012. So in the 2000s, we have the emergence of cloud-based computing, application of AI and digital deep learning to big data. We have augmented reality, we have virtual reality, we have blockchain, etc. In 2017, Gartner's list of top 10 trends included digital twins, which was defined as a dynamic model of physical system and it's basically, we have many definitions, which was pointed out by Will. But I will tell you how we represent a digital twin in a minute. But first, I want to just say about ABB and Corus. We've been a partner with ABB for over 20 years. We've had joint projects, we've had joint R&D, and we have joint marketing. You look at the diagram on the right, the red boxes and the yellow boxes. The red boxes represent ABB's X100XA platform, and it provides DCS operator stations and human machine interface models, electrical models, power management models, DCS soft controllers, and SIS soft controllers. Corus provide models and interfaces, instructor station and field operations, and 3D plant models. So we combine these into integrated solutions for our customers. Our models, as has been mentioned before, there are many versions of digital models, digital twin models, that it can be very simple. And ours are characterized by being large, complex, holistic, physics-based models that are representative of entire plants. For example, an olefins plant, the ethylene plant, the furnaces, the cold section, the utilities can all be delivered as one whole integrated model representing the actual plant dynamically, which is, I would say, on the large scale of models. And it's all based on, first principles chemical engineering models, conservation of mass and energy and momentum. And we've got some partial differential equations over there to wow you, but in fact, that's what it really is. Now, one of the applications of our solution has been operator training and also code validation. So we have this term CV-OTS digital twin, and that's where most of our business is right now, meaning that people are doing control system modernizations, where they're doing new plant construction, and they want to get an operator training simulator that can be used for doing code validation, developing APC seed models for multivariable predictive control, doing engineering studies of dynamics in the process design phase, in the conceptual design phase, the detailed design phase, so that, optimizing the workflow across teams from the left to the right across the plant lifecycle is accomplished using one version of the truth in these models. What's depicted here basically is, someone's got some feedback there. The plant at the top level is in gray and the digital twin is in pink below. And what are the elements of a plant? Well, we have the control room, the HMI where the operator sits. Then we have the control and safety systems, which is distributed control system and safety instrumented system. And then we have the actual physical assets in the process plant. For us, in the hydrocarbon division, this is oil refineries, it's gas plants and midstream, it's ethylene plants, it's olefin plants, it's polyolefins plants, and it's agrochemicals. Now, on the digital twin side, we're basically emulating or stimulating, in other words, the exact replica of the plant in software. So in the training room, we set up screens that are basically comprised of exact replicas of the DCS screens that are used to control the plant that we get from ABB. And then we have our own instructor station graphics that allow the teacher to train the various operators through a second screen. And the emulation of the control system is identical. In other words, what the operator trainees are seeing is the exact display and control system and instrumentation that they have in the field. So, I mean, when people ask me on an elevator, what do you guys do? I basically make the first analogy, well, you've ever heard of an aircraft simulator? And they all go, yes. Well, I said, well, that's what we do for oil refineries. And that's when they kind of still look at the wall and still don't know what I'm talking about. But it is true that we're giving them an environment that's identical in every kind of way. You can do startup procedures, you can do procedural automation testing, you can do control system tuning, even PID tuning, you can start up and shut down the entire plant, you can do everything you can in real or faster time on the simulator. Now, the process model on the right is just a picture of our modeling platform, but behind the scenes, there is a rigorous model that's been built up with objects that are chained together that are based on the P&ID drawings of the process. And to build those, we need data coming from other models, other sources, equipment data sheets, compressor curves. To make that plant look like the real process, we need to have data to make our modules represent those processes. Combined with our thermodynamics and our physical properties and our solvers, we chemically engineer and recreate the process plant dynamically accurately. So the topology of the digital twin has already been stated. This is a bit redundant, but it does show that we have the 3D reality for field operation, which is different than the picture I just showed you a minute ago, where it showed people inside that were being board operators being trained. Now, the use of this by engineers isn't depicted here, but this same model is used by engineers in an offline system for what-if analysis and control system strategy testing. And what the result of this use by engineers earlier on in the life cycle has been is that plants have been able to start appreciably faster. Information has been able to be exchanged among groups more efficiently. And flaws in designs and control system strategies have been detected before startup, so that not only has startup been quicker to happen, but it's been more reliable and safe when it did happen. And there are several major use cases, and this has been going on for some time. I kind of don't want to read this slide, but, and I've alluded to these already, you'll get a copy of the slide. So I would just say that it's more than just operator training. And to get the advantages of this across the plant life cycle, you need to engage with dynamic simulation early on. Typically, the front end of a process design is steady state simulation with process licensors and EPCs. The use of dynamic models, which can be used throughout the life cycle, aren't considered sometimes, and they're forgotten until it's too late. So I would say that if you're a customer out there or someone out there thinking about the use of dynamic simulation, think of it early. Okay, so what I want to do is talk about a few examples. This was a project with ABB that was the largest petrochemical complex in the world that's ever been constructed. It was in Sadara Petrochemical in Saudi Arabia. That was 26 integrated world-scale plants, 800 XA safety and automation systems with over 150,000 IO. Now, nobody's typically going to be like this, but the thing was here, it was a huge engineering task. How did we get all this ready in advance? We basically had 18 code validation OTS systems from the feed stage implemented that were delivered with 40 operator consoles across 5 control buildings. So, I mean, that's pretty major. So we worked with ABB. We employed pretty much all of our division or all of our engineering groups across the globe. And we worked with the joint venture partners to actually test the code for the control system in advance. And we started up all these plants ready. And so it was delivered on time. It's quite a monumental feat. This is a great example of, and when I say code validation, we're talking about the DCS configuration, we're talking about procedural automation, we're talking about state-based control, we're talking about not just your PFD level, final control elements of a PFD, we're talking about, automation and procedures that are going to be tested in advance of plant startup and done in time to be able to train the operations personnel and the engineers in the ongoing use of this to start up the plant and over time for the life cycle of the plant. Again, big program, BP worldwide, they're using the same concepts as the Sadara plant in the sense that actually there's something different here. With BP, a lot of their projects are for aging workforce or control system upgrades, or just they want simulators because they know they make operations safe, and it's important for them to train their operators no matter what the situation is. There's been a combination of DCS migrations and new units using 3D, using dynamic models from the custom models delivered with integrated to the various DCS systems, and they have a centralized, the way they deploy this, they have a centralized group that sort of monitors this and works with us to kind of deliver to all their refineries. But it's been it's an example of Corus being in partnerships with people for long periods of time. So ABB over 20 years, BP over 20 years, Nova Chemical over 20 years. There are other ones that are coming forth. So, I mean, why do people work with us that long? I guess it's because of our people, our approach, and our technology. But upstream offshore development, multi-physics simulation. Phil, are you on the call? Anyway.
This project is embedding an integrated model with a multi-physics approach. We were using Olga software from Schlumberger to model the multi-phase subsea network, which was linked to the Indis Plus, our platform modeling the topside facilities. So this is one example of a multi-physics simulator. On this integrated subsea process model was linked to the ABB control and safety system for DCS, SIS, virtual commissioning and early training before startup.
Thanks, Phil. And Phil, you can continue with that one.
So this one is another example of a multi-physics simulation, embedding an electrical model that was previously presented by Elise, linked to an Indis Plus process model and both linked to the ABB control system. So with this integrated model, we can transfer knowledge between electrical and process personnel, who are usually not talking each other, and we can test and optimize the power management system, taking into account a rigorous electrical modeling together with input from a rigorous process model. Then we have two examples which are not from the hydrocarbon division from Corus. This example is from the nuclear power division, where they develop a 3D digital twin for nuclear power plants field operators. Because of radiation, they cannot have training in this kind of area. So they develop a 3D replica of the virtual plant using virtual reality headset and mixing the 3D virtual reality together with multi-physics model of the plant facilities. So this the benefits are the improvement of understanding of the physics, and this this allow to verify the safety requirements through the execution of the gesture in the building within a virtual environment. And the last example is from the transportation business unit, for which develop a mobile mapping technology to scan, I would say, thousands of kilometers of track to develop a high fidelity 3D models of several thousands of kilometers with high fidelity, mapping the real world in the computer generated images. And we develop also automatic tools to recognize the patterns and to improve our efficiency to deliver high fidelity train simulators, allowing us to have an easy update of the 3D model and giving operational savings to the rail transportation end users to train the drivers. Sorry.
So ABB and Corus France, ABB Norway and Corus France have worked together for joint R&D. This slide's from Europe. I've read it. I understand what's going on, but I don't know if Elise wants to comment on some of the things we're doing.
Yes, I can. Yes, we have started this R&D project As I mentioned, the purpose is to, first of all, look at the plant state, to collect the state from the plant historian, and to feed a simulator with that collected state, so that we can have an online initial condition. And we will align the control system so that it is according to the plant state, and then it will be a job for the process model by Corus to reconciliate. So those knowing physics and chemicals will know that that is quite a big job on the modeling side. So we are thankful for that cooperation. And when that is done, this online simulator can then be used for several purposes. So we think about that we can generate data and to have also machine learning on a future in the future state, so that we can have more learning from the behavior on the plant. If we can see some patterns in the process that should be taken into consideration, and if there's for example, if the operator wants to do a PID setting, perhaps then the machine learning can tell that this is not the best way of action. Or you can say that, for example, with the setting, you can have 3 scenarios. So these are the ways this process will behave. So then the operator can have a trial and error before taking a setting into action, for example. So these were some topics. Thanks.
Thank you, Elise. That's very exciting.
It is.
Yeah.
Perhaps
Okay.
Lars has something to add. I don't know. My colleague from ABB. But
no, I'm fine, Elisa. Thank you.
Okay, thanks. Yeah, thanks from us.
So this gets into the left side of this diagram, which is called the ultimate digital twin, the UDT. But you know, our customers are asking, hey, can you run your Indus Plus model and take data from Pi and or IP21 or whatever and put it inside of your Indus Plus simulator, and then do what if cases or run it in a parallel model to do predictions or the look ahead. And there, as Elise mentioned, there are some process modeling, heavy lifting there to get that to work. However, I'm glad that our research is focused on that, and because this is a demand from the market, and I think it has a lot of value if we can progress it to be applied to these large-scale models that I alluded to. The whole ethylene plant, the FCC plant, or all the naphtha complex of an oil refinery, or a whole ammonia plant. Conceptually, it's easy. You say, hey, I get the data, I do some data reconciliation on it, I pull it in to my process model as inputs, and then all the outputs should come out. And in theory, that's kind of correct, but there are also some internal parameters and things that we don't read in from the historian that need to be initialized in the model that that's the trick, right? So we'll probably, I don't know what process we're starting out with. It's probably a distillation tower or something fairly simple, but to apply this to an entire ethylene plant would have, what's the value? Is anybody really interested in that? Can you really use this in a real, in a way that actually gives you the benefit, or do you want to decompose it into smaller parts and just do it in certain areas? So, but it's what people are demanding. And Phil, this is your slide. Do you have any comments on UDT?
UDT, you have the online first principle digital twin, which will receive the duplicated command from the real plant data. So the DCS opening, valve opening, start, stop commands which will be duplicated. So the online digital twin will follow the same, will receive the same command, or should follow the same path as the real plant. And from this online first principle digital twin, we could take a snapshot at any time and to initialize the offline first principle model, to run it offline, to perform look ahead, what if studies, or operator training. So this, with this online up-to-date first principle digital twin, this will allow us to have a simulator continuously updated in line with the real plant status. From this online first principle digital twin, we will also generate a lot of data. This simulated data could be compared to the real plant data for sure, but they will provide also virtual sensors. And this pool of data, which are complementary to the real sensor, could also be sent to a machine learning or deep learning algorithm to generate even more data and to give more data for data-driven digital twin. So, for example, if in the real plant you have 10,000 IOs, transmitters basically, in the first principle digital twin, we will have access to all pressure, all temperature, mass flow, composition, which are computed in high fidelity and with rigorous algorithms. So you will have a lot of data which will be available from the online simulator, which are not available from the real plant. So you will have a huge amount of data. So with this additional data, we could discover additional patterns which are not accessible from the real plant data. In addition to this first principle digital twin, we could have also a 3D digital twin with same principle, receiving some command from the real plant, like manual valve position or other command from the real plant could be sent to the 3D model to keep the 3D model up to date also, and to do what if study or whatever from the offline 3D digital twin, which could be coupled for training with the offline first principle process model. So that's
okay.
an overview of the ultimate digital twin on a conceptual basis.
I know we're probably out of time. I just would want to make one final comment. So we're talking about it could be, would be, future. You can right now with an historian in our simulation models actually perturb the inputs over a response surface to generate outputs that could be used for deep learning models to build an AI model of a process. It's different than saying, let's take plant data and initialize our process to match the plant and run it in real time. This is just something like we have a wealth of first principles models sitting on the shelf of all industrial processes for the industries that we're in that are basically could be the version of the truth, right? The real plant without having to have the real plant. Because most plants operate on a single point or a couple operating modes. There's not a lot of variance in their inputs, but with our models, we can exercise them to go anywhere. Okay, I think that's it. We got some references, which you'll get in the slides, some papers, links, and that's our presentation. Thank you very much.
Great. Philippe and Greg, thank you both for the presentation. Those are some exceptional examples of digital twin applications. I particularly like the stroll down memory lane for the evolution of industrial control systems and also the fashion industry. I thought that was fantastic. The Sidera model was a massive project too. I can't imagine the amount of inputs and outputs you guys had to deal with there. So kudos to you on a successful journey there. Now, I'd like to transition to our Q&A portion of today's session now, so we can entertain some of the questions that are coming in from the audience. Now, several of you have asked about the content from today's session, and yes, it will be available after the virtual conference today. You'll be receiving an email shortly. We still have two options for submitting questions today. You can use the Zoom Q&A tool, which most of you have found, and you can also submit them via Twitter. Now, we've had great engagement thus far. I've got a lot of questions, and we're going to do our best to address them live in the time remaining. But in case we don't, we will carry this conversation over to Twitter using hashtag IIoT World, WORLD. So I think I'd like to kick off with the first question that came in. This is around, there were several questions that actually came in around this topic, talking about standardization. Are there any organizations working to define digital twin standards? And are there canonical data model standards or other initiatives to help develop easier digital twins for IoT applications? So I'll throw that out to the collective and see who'd like to grab that first.
So I can just jump in quickly. There is an ISO committee that is working on a digital twin standard focusing on manufacturing Unfortunately, right now it's under development, but it's a three-part standard. That part one is an overview of general principles. Part two is reference architecture for digital twins in manufacturing. And then part three is a focus on the digital representation of physical manufacturing elements. So that's something that is currently in the committee part of the ISO standard lifecycle. But maybe some of the other presenters have a little bit more information on that or other standards.
Well, that's a great place to start then, at least if ISO is working on it. Anyone else care to comment before we move on to the next question? Okay, hearing none. This came in from Scott. This is an interesting one, actually. It says, when might a digital twin solution not make sense? Is there ever such a scenario?
So
I'm hearing crickets.
I would say
no, Scott.
Yeah, I actually think no might be a reasonable answer for that. The thing is, once digital twins, the technology and you know the standards come out and people really understand how to apply them, for those applications where you might think, oh, this is maybe too simple for a digital twin to really be effective. Well, those are also going to be applications where it's much easier to deploy a digital twin to begin with. And so even if you're not using a digital twin to maybe optimize a process, there are a lot of options for using digital twins to enable things like services. So I think probably right now there are plenty of examples where it's not a good idea to start building a digital twin, but I think down the line, digital twins are going to make sense for just about every type of asset or process.
Okay, thank you, Will. Any other thoughts on that one? Okay, hearing none. Now Sam has an interesting question. How can you create digital twins for greenfield assets that have gone through many process or construction modifications?
Painfully.
Yeah. So I would say ideally the digital twin, the concept is there from the beginning. So these changes should be captured as part of that process. If they're not, those changes likely are part of an engineering change order type process. So there's that information there. It's just a matter of figuring out a way to incorporate it. And that process is something that's being understood and developed by ISO standards.
Okay. Now we've got a vernacular
Peter, you want to comment on that? I mean, we have projects in this situation. And what we're stuck with not having the data we need to build the model, so we have to come up with it somehow.
Yeah. This is Lars from ABB. In our projects, I mean, the process model that undergoes changes over time, of course, and there are freeze dates where we have builds, and finally, eventually, there is also an as-built project, so that the model will be updated with the real how the plant actually evolves into. And the control system part of our digital twins is, of course, a replica of the real control system. And we work with dumps and import-export functionality from back and forth from production system to simulator system. So it's quite easy to update and keep up to date.
Right. So on the process side, you may have mechanical drawings or vendor data that you don't have access to. It might be a PDF file. It might be stored in a box somewhere. The drawings may not be updated, but certainly the DCS configuration will represent what's out there, but there might be some field instruments that aren't documented well. So, I mean, it's something you have to strive. And then as was alluded to, this management of change, as things do get changed, they should be put in and updated to the as-built so that you have a working live system moving forward from a project you may do.
All right, thank you. I got a question from Patrick along the same lines. What is the adoption curve for digital twin platforms being put in place for brownfields? What challenges do brownfields have, if any, to get a full digital twin platform like Norway Oil and Gas Company examples?
Management buy-in, funding. the drawings not being up to date, timing, getting it started at the right time, and understanding how it all fits together with the contractors so that you don't start too late?
Yeah, so another big part of that is what was alluded to before is getting that CAD data. So oftentimes what we see with brownfield projects that want to have a 3D representation of the site, they'll use either 3D scanning with LiDAR-based scanning or photogrammetry, and that at the very least gives them you know, the shell of the site to start tagging things and doing things like that.
Got it. Okay. Here's an interesting question from Joy. It says, do digital twin have any design and implementation impacts and issues as they're shifting from cloud to edge computing? So I think what she's after here is how is the cloud to edge shift affecting digital twin technology and implementation?
Well, one big aspect of that is being able to determine what data actually gets fed to the cloud and what data gets stayed on the edge. So that I'm not an edge tech expert. We do have those here at ARC. But there are applications that are being deployed at the edge now to filter through data and to discern what's valuable enough to go to the cloud and what's not. And that really helps with things like bandwidth. And so really kind of controlling that flow of information is really critical.
Pretty foggy question.
Mm-hmm.
All right, she's got another one. It says, how can digital twin help plant operators act more like a process engineer or maintenance engineer in a day in the life scenario? Could you please provide the benefits and the areas of engineers' activities it can replace?
Well, if the operators are allowed to tune loops, that's one area. If you shift the operator from thinking about controlling flows and temperatures and have them shift to economic values or optimization variables, they could actually start to optimize their unit on their own in the control room without process engineers. I mean, that's pretty much of a stretch, but I mean, that is possible, right? They have access to a tool that allows them to take the paradigm up of what we're actually trying to accomplish in operations, from prescriptive targets on final control elements to sort of high level optimization targets in business.
Yeah, I agree there. And we have some customers that have a simulated system in the control room so that the operators, of course, an offline system then, or standby system, so the operators can go there and do tests and see and play around. And by that day, I think they can also learn from that. So that is one aspect.
We've got a vernacular question coming from Dave. He says, digital twin versus administrative shell. Are they the same thing, or what's the difference?
I can chime in here. That's actually, I saw that question. I thought that was really interesting. One of my coworkers, actually, Valentin Delou, wrote a blog and a white paper at the end of last year on administrative asset administration shells. And I was reading through it, and there certainly is a lot of overlap. And I don't think anyone that any blog or white paper that I've read has really kind of tried to make a distinction between the two. I would say that the asset shell doesn't try and take a look at the entire process of a plant. It's very much focused on singular assets. So I think you could make the argument that a digital twin of an asset and the asset administration shell are maybe one and the same. But then when you take that higher level look of an entire plant, that's where the concept of an asset administration shell kind of breaks down. Maybe a digital twin is the summation of many of those. So I think that's still an area that's maybe worth exploring a little bit more. Good question though.
Excellent, thank you. Well, then I think we're going to end on that note. It is the bottom of the hour, and I want to thank everyone for taking the time to join us and thank our speakers. Please stay tuned for other educational webcasts brought to you by IIoT World. And I'd like to invite you to save the date for a special day. It's IIoT World Global Day. It's June 30th, 2020. It will be the largest industrial IoT virtual event in the world. A full-day virtual summit dedicated to accelerating the rate of adoption of industrial IoT. Now make a special note to register for free, yes, you heard me right, for free now at www.iiotday.com. And you'll save the $499 registration fee, which is going to go into effect very soon. That's your bonus from us today for attending. You can also secure briefings with our editors, analysts, and co-founders during the upcoming event, ARC's Advisory Forum in Orlando, Florida, that's next week, and Light and Building in Frankfurt, Germany, March 9th through 13th, and Hannover Messe in Hanover, Germany, from April 20th to 24th. Special thanks to our sponsors today, ABB and ARC Advisory Group, for today's educational session. If you have a suggestion for a topic or otherwise, we always welcome feedback, so please drop us a message and let us know. And if you like what you heard today, we invite you to subscribe to our newsletter, YouTube channels, and follow us on Twitter at IIoT_world. This concludes our program for today. Thank you for joining us.